Okay, so in this week we will start some truss problem which were discussed in the last week. So let's do some problems. So I picked some sample problem, but before that we will try to understand how this truss problem will built and how we can implement in MATLAB. So for that we will take very simple example. Suppose we have a bar like this. And here it is x-axis, here it is a y-axis, and this is the inclination of this bar, that is theta. And suppose this, if you take this axis as another coordinate like x bar and perpendicular to this, I can assume it is a y bar. Okay, so we saw that any displacement along x-axis of this bar and y-axis along this y-axis will be given as dx cos theta plus dy sin theta equal to dx bar. Okay, so here dx bar is nothing but the displacement of this bar along x bar axis. So because of that resolution of the coordinate, I can write this by this equation. Similarly, along y axis I can also write dx sin theta plus dy cos theta equal to dy bar. So in the matrix form or in the vector form, I can write dx bar dy bar as cs minus sc vector dx and dy, and c and s is nothing but the cosine of theta, and s is nothing but the sine of theta. Okay, so now we can see that if there is a deformation or there is a displacement along this axis, this original axis, then by the use of this transformation matrix I can write the displacement along this axis, this new axis. Similarly, if you are not considering this original axis, x axis and y axis, then the same problem which we already solved along x bar and along y bar is given by this matrix function or this matrix equation. And here if 1x is nothing but along the x-axis, but 1 and 2 are nodal points. So you can see that every force will be only along x-axis. So that's why we can write this whole equation as kd equal to f, or if it is along that x bar or y bar axis, then I can write as d bar and d bar f bar. So now, but the problem is we have to find displacement not along x axis, x bar axis and y bar axis, but we have to find along x axis and y axis. So what we will do is, again we will use the transformation. Okay, so we saw that if we want to transform this displacement of each nodal point for 1 and for nodal point 2, then the same equation we can also write another matrix form like this. Okay, so but the problem is we need to change this stiffness matrix. This stiffness matrix is not same as this stiffness matrix, because we are considering all this displacement and force vector along this global coordinate axis, not in this local coordinate axis. So we need to find k underscore so that we can solve this problem. So in the class we already saw that the original this displacement matrix or displacement vector we can also write in the matrix form as this. So this matrix is nothing but the transformation. This matrix is nothing but the transformation of this displacement matrix. If you multiply this matrix by this displacement, then we will get the localized displacement, which is x bar and y bar. And similarly we can also write for the force vector also. So when we move from left hand side to right hand side, then the original stiffness matrix will be nothing but T transpose K bar and T, and this T is nothing but this transformation matrix. So which means that the original stiffness matrix, if you multiply post by T transpose and pre by this T matrix, then we will get global stiffness matrix in the original coordinate axis. So which means that we can solve our problem very easily, and now I can finally write F equal to KD, and we will solve We will take one example like this. In the previous example, which we already created a picture. Suppose we have theta equal to 30 degree, then which means that c equal to cos 30 degree and s equal to sin 30 degree, and cos 30 degree is nothing but root 3 by 2 and sin 30 is nothing but 1 by 2. And if we if you write C, S, everything here, and if you populate all this C and S in terms of this matrix, then we can also write like this. K bar I can write AE by L, and it is C square CS minus C square minus CS S square minus CS minus S square C square CS and S square, and this whole lower triangular part is nothing but same as this upper triangular part, so I can write symmetric part. So which means that now we can solve our problem. So when we substitute C, S and theta, then we will get our stiffness matrix is like this. Suppose in this problem theta is 30 degree, A equal to 2 meter square, E equal to 30 into 10 to the power 6 Pascal, and L equal to 60 meter, then we will get 2 into 30 into 10 to the power 6 divided by 60, and this matrix will be 0.75, 0.433 minus 0.75 minus 0.433. Similarly, this will be our symmetric part, and remaining part will be 0.25 minus 0.433. This will be minus 0.25, 0.75, 0.433 and 0.25. So this will be our stiffness matrix. So we already got our stiffness matrix. Now we can solve our problem very easily. Now let's take a different example like this. So here in this case, there are two bar 1 and bar 2, and it is saying like cross-sectional area of bar 1 and bar 2 both are same, which is 5 inch square. Modulus of elasticity is 1 into 10 to the power 6 and L is 100 inch. Then we have to find the displacement of node 2. So in this problem we saw that theta for bar 1, this is a problem number 1 and this is problem number 2. Same problem but different graph. So in this case we can see that theta 1 is 45 degree, and theta 2 here you can see that I am measuring each angle by this coordinate axis, and anti-clockwise direction, the angle from anti-clockwise direction I will take it as a 45 degree, as a positive, and clockwise direction I will take it as a negative. So here you can see that theta 1 is 45 degree, and for this theta is nothing but 135 degree. So here it is 135 degree. Okay, now to solve this problem, we need to find all the connectivity and all nodes. So here there are here you can see that here it should be element. Here you can see that we have two elements, element 1 and element 2, and element 1 has connecting points, or you can say that node are 1 2, and for element 2 connecting nodes are 3 and 2. And also we can see that u1 for here from the same nomenclature, we will use the same nomenclature as sir has taught us. So for node 1, we have u1 equal to 0 and u2 equal to 0. Similarly, for node 2, you can see that u1 here 1 2, then we need to write it as u3 and u4. So u3 is not equal to 0 and u4 is also not equal to 0. And for node 3, we can see that here u5 equal to 0 and u6 is also equal to 0. These are displacement boundary condition. Now we will see force boundary condition. So here we can see that F1 is not equal to 0, F2, or we can see that only at node 2, only F, you can see that here 1 2 are unknown, 1 2 3 4. Okay, x axis is a third number of force and y axis is the fourth number of force. So which means that F4 is known. F4 is what? 10 KIP. We will forget this unit and we will try to solve this problem. Okay, so yeah, so every data we have noted. Now we will go to the MATLAB code. So here I have created a MATLAB code. So we can see that if we talk about this problem, so here node equal to nothing but the coordinate. Here you can see that this is the node number 1, this is the node number 2, and this is the node number 3. So I have to modify this code. So you can see that at node number 1 we have to note its coordinate. So you can see that the node number 1 is at origin, so I have to write 0 0. Now at node number 2, I have to write the coordinate of point 2. Say, so actually I have already created a code specifically for this problem. So here, yeah, you can see that now I have to write the coordinate, which is nothing but the x value and y value of node 2. So here you can see that if we measure this x axis then y axis length, then this x axis length, because it is saying that x axis length, that is nothing but L. So that's why I have written 100. So I think I have made some mistake. So yeah, L. So I have to modify this code. Yeah, so here you can see that at node number 2 I have to note this x-axis length, and that is nothing but 100. So yeah, that is 100. Now at y-axis length, so what will be the y-axis length? So here if we note it, then I can write tan theta. Tan theta equal to perpendicular means y divided by base. So which means that will be y equal to L tan theta. So what will be the y coordinate? Y coordinate will be 100 times tan d, and that is 45 degree. So here we have to be very careful, because I am using tan d, which means that it will take degree as an input. Okay, so then it will give a correct value, otherwise it will take the input as a radian. Okay, so that's why we cannot write it. Okay, yeah, so here we can see that that is x axis, that x coordinate of node 2 is L, and y coordinate of node 2 is y equal to L tan theta, and L is what? L is this length. This is L. Okay, so that we have to determine. Yeah, so now we will move to the node 3. So node 3, we can see that x axis, the length of x axis is 2 times L. Okay, so here we have to write 2 into 100, 2 into 100, and y coordinate is 0. Okay, so now this is the nodal coordinate. Now we have to change the connections. Okay, so here we have to write connecting point, I mean connecting node for each element. So if we talk about the element number 1, so which means that the element number 1 has two nodal connecting point, that is 1 and 2. So I have written 1 and 2. Now for node 2, so here for node 2 we can see that is connecting points are 2 and 3. So here we have to make it as a 2 and 3. Okay, so this is the nodal connectivity. Now we have to change cross sectional area. So what is the cross sectional area? Cross sectional area is 5. And what is the modulus of elasticity? That is 1 into 10 raised to the power 6. So I have written. And now it is saying what is the degree of freedom. Degree of freedom, which means that nothing but those displacement which are non-zero. So here you can see that this u1 and u2 are already 0. So I cannot write u1 and u2. Okay, so here we need to not write u1 and u2. Okay, now u1 u2 are gone now. So here u12 only 3 and 4, only 3 and 4 will survive, and u5 and u6 will also gone because it is also fixed. So that's why there are only 2 degree of freedom, that is 3 and 4. Okay, so now n is nothing but the number of nodes, so which we can get by using the size function, of this node. Okay, and here the number of total degree of freedom, that is nothing but the 2 times nn. Okay, so that's why we'll get 2 times nn. Okay, and ne is the number of elements, so we already got. Now we have to initialize global stiffness matrix, and similarly for F. Okay, now we will move to the what is the force boundary condition. Okay, so here you can see that the force boundary condition is only at node 2, so which means that we have to write F3. F3 is 0. Okay, so F3 is 0. We have to write F3 as 0. F3 as 0. And F2, what is F2? F2, we can see that not F2, F4. F4. F4 is what? That is completely in upward direction. Okay, that is completely in upward direction. So here I can write 10. So this is the force boundary condition which are imposed only at node 2. So that's why I have written F3 equal to 0 and F4 equal to 10. Okay, so here also I can modify it as F3 equal to 0. Okay, so now this code, we can run this code, and before running we will try to understand what it is doing. So what it is doing is, for each element whatever we are given, for each element it will try to find the length of the bar and sine and cosine of that angle. Here you can also think like why we are using this form. We can also write as a C and S. So here why I am using it, because this is a very general code, and this code can be used by any kind of truss problem. Okay, so only we have to write the coordinate. Okay, so later it will also find L and M, that is nothing but sine and cosine. So here it is a local stiffness matrix which we always earlier saw, that is this matrix. Okay, and now we will try to run this code. So here you can see that after running this loop, we can see that it is giving for element 1. For element 1 it has given this stiffness matrix. Okay, now we will also run. So again we will write, continue. So here you can see that it is also giving the stiffness matrix for element 2. Okay, so there are only 2 elements. Now we will continue. If we continue, then it will give a global stiffness matrix. We can see that for element 1, for element 2, for element 1 and for element 2, this is the stiffness matrix and this is the global stiffness matrix. Okay, so now we also have to find what will be the reduced. So what will be the reduced? Because we already know that only F3 and F4 are known, so because of that only that part of the global stiffness matrix we can take, and because of that this will be the reduced global stiffness matrix and this will be the reduced force matrix. Here you can see that F3 equal to 0 and F4 equal to 10. So after solving the equation, we can get as a displacement of node 1. We can see that the displacement of node 1 is 0 and y is also 0, y coordinate is also 0, and for node 2 we can see that it will move towards left by this unit and by this unit. Here we can also find what is the reaction force at node 1, 2, 3. Here it is only find 1, 2, 3, 4 because we already know that at F3 and F4. So this is what F1, F2 and F4 and F5. Sorry, F5 and F6. Okay. So this is what will be the strain. What will be the strain at each element. So this code can be used to find the stiffness matrix and the displacement, reaction force and everything. Okay, so now for this problem we will move to this problem. So I have already created the same code I will use, but only I will modify. So yeah, so in this code you can see that again I have to do the same thing. So here there are how many nodes? 1, 2, 3 and 4 nodes. So for each node we have to write coordinate. Okay, so yeah, so for node 1 it is at origin. For node 2 here I have to write what is the coordinate. So x axis, so here the x axis is nothing but 100 into tan d. Tan d, what is that? Again we have to do this same thing. Suppose here theta, so tan theta equal to x divided by L. So if you want to find x, then there will be L tan theta. Okay, so yeah, so 100 tan 30, 100 tan 30, and what will be the y coordinate? So that is y 100 only. Okay, now for node 3, so for node 3 we can see that x coordinate is already 0, and what will be the y coordinate? Y coordinate is 100. Okay, similarly for node 3, so x coordinate will be the same but in the negative direction, so minus 100 into tan d 30. Okay, and what will be the y coordinate? Y coordinate will be the same, that is 100. Okay, so yeah, now we have to write what are the connecting elements. So if we are considering this as element 1, element 2 and element 3, there are 3 elements. So for element 1 that is 1 2, for element 2 that is 1 3, 1 comma 3, and what is the connecting points for element 3? That is 1 4. Okay, again A is same, E is same, but we have to check what is the degree of freedom. So degree of freedom is only at point 1, so that will be 1 and 2, because here you can see that 2 point is fixed, 3 point is fixed, 4 point is fixed, which means that their displacement will be 0, so that's why we are not writing here. Okay, now there is a force boundary condition. The force boundary condition is also at point 1, so that will be F1 and F2. So what is the F1? F1 I can clearly see that is 141 into cos d 45 degree. Okay, and what is the F2? F2 is 141 into cos d 45 degree. Okay, now everything is fine. Okay, yeah, here it is should be capital F. Okay, now everything is correct. Now we can run and we will see our results. So here we can see that this is the stiffness matrix for element 1, for element 2, for element 3, and this is the global stiffness matrix, and this is the reduced global stiffness matrix. This is the forced, this is the forced stiffness matrix. Okay, forced vector. Okay, and this is the nodal displacement, that is for okay, I think we have made some mistake here. Okay, what how many nodes are there? 1 2 3 4. Okay, the coordinates is 0 0. For 2 that is 100 tan 30 and 100, this is 0 100, this is minus tan 30 and 100. Okay, fine. What is the connecting points? 1 2, 1 3 and 1 4, and what is the degree of freedom? 1 and 2. Okay, it's correct only. We will run it again. Okay. Okay, fine. So here we can see that the displacement at node 1 will be this, and at every node, which means that at node 2 0 0, node 3 0 0, node 4 0 0, and reaction forces will be at node 1, that will be in x coordinate. You can see that this reaction force is nothing but the resolution. If you resolve that, this force along x and y axis, then you will get the same value. Okay, but for node 2 we can see that negative negative 0 and this kind of thing. Here it is clear that there will be no reaction force in x axis, so that's why it is coming out 0. Okay, and this is again for this. Okay, and this is the for strain and stresses. So we can see that this code is working very fine, and before that we will take a 5-minute break and we'll come again. Okay, so let's start. Okay, so we will also try to solve the same problem which Sir has discussed during the class, and we will try to solve using this MATLAB code. So the question was like this. We had a hinged point here, and here there is a roller, and here there is also a hinge point. Oh, I think I have to see that.
Element length is
Yeah. So yeah, this was the problem, and this height was 30, and this we are considering, okay, this was like this, and this horizontal length was 40, and this we are considering link 1, element 2, element 3, element 4, and nodal coordinate was like this: 1, 2, 3, and 4. And there was a vertical force that was F equal to 25,000 Newton. Okay, and here also there was a force that is 20,000. Okay, 20,000 Newton. Okay, now we will try to solve the same problem by using our code. Okay, so I have already created this. Yeah, so here you can see that, we'll take it to this separate. Yeah, so here you can see that first I have to make the nodal coordinate, that is for node 1, which are at the origin 0 0, for node 2 that was 40 comma 0, for node 3 that was 40 comma 30, and for node 4 that was 0 comma 30. And what are the connecting nodal point for each element? So here for one element you can see that the connecting points are 1 2, and for node 2, for element 2 that was 2 3, for 3 that was 3 4, and for element 4 that was 1 3. Okay, okay, yeah. So area So what was the area? Area, we need to see what was the area. Yeah, area was 1 and modulus of elasticity was 29.5. Okay, fine, everything is correct now. Okay, now we need to see what are the degree of freedom, which means that what are the node, which nodes which are at zero or non-zero displacement. So here u1 and u2 are at zero displacement, okay, but u3 and u4, okay, u3 is non-zero because it can slide along horizontal direction, but u4 will be zero because it is constrained to move in the vertical motion. Okay, so 3 we can write here. Now for node 3, so for node 3 we can see that that will be u5 and u6, so that's why I have written u5 and u6. And for node 4 every displacement is 0. Okay, so yeah, so here we have to initialize, we have already initialized. Okay, now we need to write what are the forced boundary conditions. So here you can see that at f3 at which is at node 2, what are the forces? F3 and F4. So here we can see that what is the F3? F3 is 20,000, okay, but F4 is unknown because it is constrained to move in the vertical direction, but it can take a reaction force, so that's why F4 is not known. Okay, similarly for F5 and F6, so F5 is we don't know, but F6 which is in the vertical direction. So here we can also write, we can also, if it is not given, then we can also write F5. F5 is 0. Okay, F5 is 0, but F6 is 25,000, which we can write minus 25E3. Okay, so everything is correct now. Now I can run this code. Okay, so yeah, so for the stiffness for the element 1, this will be the stiffness matrix. For element 2, this will be the stiffness matrix. Element 3, this will be this. So these are the stiffness matrix. So now, so these are the nodal displacement. For node 1, you can see that u1 and u2 will be 0. For node 2, you can see that vertical displacement will be 0, but there will be horizontal displacement. Okay, similarly for node 3, there will be a nodal displacement along x-axis and y-axis. Okay, but node 4 is fixed, so that's why 0 0. Now if you if you talk about the reaction forces, so yeah, there will be a reaction force for node 1, so that will be this. And here for node 3, we can see that for node 3 we can see that there is no horizontal reaction, so that's why it is 0 0, and there is a vertical reaction, that is minus 25,000, and this is the stress and strain. Now we can verify what result sir has arrived. Okay, so if we run, oh yeah, so this is the so now we will solve the assignment 4 problem, which is given as below, and it is saying that there is a stepped bar which consists of two material 1 and material 2, and material 1 is of length 7.5 meter, material 2 is a length of 6 meter, and different cross section areas, that is 0.4 meter square, 0.25 meter square, and their Young's moduli are different. And also at the right end of the right portion of the material is actually connected with the spring constant of 2 kilonewton per millimeter, and it is saying that we have to use two quadratic bar elements, and it is also written as we need to create 5 nodes, and each has a coordinate, and each element must be 3 nodes. And here we can see that node 3 is at this location. So what we will do is, we have to suppose this is the stepped bar, and this one is a different material. Okay, so it is saying that we need to create 3 nodes. We need to create 3 nodes at each element. So like this. So let's suppose this is the node number 1, node number 2, node number 3, node number 4, and node number 5. And also this node is connected to the spring with the spring constant 2 kilonewton per meter. Okay, so then we have to find stiffness matrix, element stiffness matrix and global stiffness matrix, then we will solve the problem. Okay, so yeah, so in the last class, sir has already told us that in this problem, the variational using the variational method, we got this kind of equation, that is -1 to 1 a e and du by dv by dx and du by dx dz, sorry, dx dx equal to, since it's already given that there is no such weight, or you can also say that there is no such effect of the weight of the bar, so in that case we will ignore that. So the final is ae du or dv by dx, not dv by dx, it should be du by dx, du by dx -1 to 1. Okay, so with the variational statement we get this equation, and if you write v for the element wise, if you write ve, then we can write easily that ve equal to nothing but n v cap e, ue is n u cap e, and yeah, and xe is n x cap e. Okay, so if you take the derivative dv by dxe, then we got that b by j and ve. Okay, similarly du by dx, it should be e, and this will be also b by j and u hat e. Okay, so these were the all equations. Okay, so if we substitute all those, so we got v e transpose, okay, and minus 1 to 1 a e b transpose b divided by j del zeta equal to v transpose e, and it should be at, okay, v transpose e, and if you write it here du by dx, then we get a e. Okay, actually it should be v also here. Okay, so I missed that, so that will be v e transpose a, it should be n a e d u by dx minus 1 to 1. Okay, so these were the equations. So we can write minus 1 to 1 a e b transpose b divided by j del zeta equal to n a e du by dx, okay, minus 1 to 1. So this is the our final equation. Okay, yeah, I missed one more thing, that is yeah, here, that is ue, okay, and here it should be ue matrix vector actually, so it will be ue. Okay, yeah, this is the Gornick equation, so that we can write ku equal to f. Okay, so now but the different condition here we already saw that is this point, this node 5 is actually connected with the spring. So suppose at node 5, I'm talking about at node 5, at node 5, so this is the node 5. Suppose u5, I'm considering u5 is greater than 0. If u5 is greater than 0, which means that this spring will be compressed. This spring will be compressed, and at the same time, because of the Newton's third law, this spring force will also act a force on this bar element by Fs. Okay, so which means that suppose this bar element is also apply a force F5, okay, F5 or at this point, which means that this F5 is no longer same as earlier whatever we solved, which means that this F5 will become this F5 will not be same as that, so which means that while solving this problem, this will become F5 tilde, and that we can write F5 minus Fs. Okay, so that I can write F5, and what is this Fs? Fs, which means that is nothing but if it is a spring constant k. Okay, so this will be k times u5, whatever the displacement at point 5, that will be u5. Okay, so which means that if we create a matrix, that is global stiffness matrix, that in this case that will be 5 by 5. Okay, and here it will be u1, u2, u3, u4, u5, and here it will be whatever will the entry here 0 0 0 0, but at the place of Fs, what we have to write? Fs minus ku5. Okay, so which means that when you when you move this thing here, or you can say that we can also write like this, k times, I mean 0 times u1 minus 0 times u2 minus 0 times u3 minus 0 times u4. Okay, so in this case we can move here this part we can move, this part we can move on the right hand side. And when you move it, when you move this part, then whatever is the populated matrix here, but this this element this element is nothing but k5 5, and this element will be modified, this element will be modified by this. Okay, so plus this will become ks. If I am considering this is ks, then it will become ks. And now you can solve this problem as it is. Okay, and this will be whatever will be 0 0 0 0, and whatever the entry, if you apply the boundary condition here, suppose if there is a boundary condition, in this case there is a boundary condition here, force boundary condition, and that force, what is the force boundary condition? In this case that force boundary condition is 10, I think P equal to 10 kilonewton. Okay, so here I have to written 10 kilonewton and 0 0. Okay, yeah. So this is how we have to solve, we have to tackle this problem. Now we will go to the MATLAB program and we will see how we are doing this problem. Okay, so yeah, let's go. So I have modified the same problem, whatever we have solved in assignment 3 and 2 and 3, and we'll little bit modification. Okay, so yeah, so here we can see that x equal to we have to take quadratic element and with 3 nodes. So here we can see that these 3 are 3 nodes. Okay, and here these are another 3 nodes. Okay, and the 3 point node 3 is actually connecting node. So here 1 2 3 nodes, and for other element that is 3 4 5. Okay, and here these are same, and we have to take quadratic polynomial, so that's why degree will be 2, number of points per element will be 3, and here it is a normal boundary condition we are taking as a 10 kilonewton, that will be applied here. Okay, that will be applied here. Now here we made some small changes, and what is that change? The change is the area and Young's modulus is actually changing. The area and Young's modulus is actually changing when the length is at 7.5. Okay, so when length is less than or equal to 7.5, so which means that this condition will hold. When length is 7.5, this condition will hold. Okay, and when length is more than 7.5, this condition will hold. Okay, then it will calculate stiffness matrix. It will take argument as a degree, local coordinate, number of point, and this a and e will go inside the stiffness matrix function. Okay, so this is the stiffness matrix function. You can see that it is taking degree, nodal coordinates, number of points, a, e. Okay, then it will also calculate shape function matrix, Jacobian it will calculate. Okay, then using the Gauss quadrature it will find the Gauss points. Then this is the integrand. Okay, this is the integrand. You can see that is AE B transpose B divided by Jacobian. Okay, then it will find the local, or you can say that element wise stiffness matrix. Okay, so which means that for each loop, for each element, it will compute stiffness matrix. Okay, and then now here is also a condition. That is a force boundary condition, and because of that we have to also apply if statement. Okay, what is that? If local coordinate if local coordinate, which means that for each element, okay, if the local coordinate of a particular element, okay, and if the end point is 7.5, what does it mean? If element, the end point, that is 7.5, then what it will be? The F local will be compute force matrix, and it will give a boundary condition, that is a force boundary condition. It will take a force P, and what is that? We have already taken as P as a 10 kilonewton. Okay, then it will take a 10 kilonewton. Else, if that is not the element, then it will take a 0. We will also see what is that force matrix. Okay, this is the force matrix. Here you can see that it is taking a degree, that is 2, and if it is a P, okay, if there is a value of P, then it will calculate here. Here you can see that is nothing but N transpose, here N transpose P. Okay, so yeah, where were we? Okay, yeah, here. Okay, so F local we will determine. Now it will find a global stiffness matrix. So here you can see that for each element it will add local with the global. Okay, and what is the global here? We have already initialized what is the global matrix. Here all elements are 0, so it will be populated when the loop will run. Okay, so up to this point we will try to run this code. Okay, here, yeah, so here we can see that for element 1 this is the stiffness, local stiffness matrix. Okay, and this is for the element 2. Okay, now it will display a global stiffness matrix. Okay, what happened here? Here this matrix will be added in the all 0 element matrix, and this will be also added, and here these two elements will actually add up. Okay, because the node 3 is actually connecting node. Okay, so that's why we will get this global stiffness matrix. Okay, here we need to be very careful that here till now we have not added the effect of spring. Okay, now if we run here, now the spring effect of spring is coming into the picture. Okay, what is the spring constant? Spring constant, we will see what is the spring constant. Yeah, 2 kilonewton per millimeter. Okay, so which means that will be 2 into raised to the power 10 raised to the power 6. Okay, so now what I am doing is I will modify the global stiffness matrix. Okay, I will modify the global stiffness matrix. First, what I have done is I have stored this value in this, then I will add 5 element. Okay, index 5 I will add with the spring stiffness, that is this, and this will be stored in the global modified matrix. Okay, so this will be the global modified matrix. Okay, now it will display. Yeah, here you can see that there is some small difference. Here it is 1.944, here it is 2.144, and that is happening because we are adding 2 into 10 raised to the power 6. Okay, now it will also calculate F global. Here it is a F global. We saw that we can see that it is added 10 kilonewton at node 3. Okay, now what we are doing is, now everything is done. Okay, we got K global modified and we got F global. Okay, now we will partition the matrix. Okay, and how we will partition? We will partition like this. Okay, I will tell you how we will partition. We will partition like this. Here it is U1, U2, U3, U4, U5. Here it is F1, F2, F3, F4, F5. Here you can see that this term, this is actually 0. Okay, this is actually 0, and these 4 are actually unknown. Okay, then which means that we need to solve this partitioned matrix. Okay, that is 4 by 4. Okay, and here what are known here? F2 are 0, F3 are 10 kilonewton. Okay, F4 are 0, F5 are 0. Okay, so here you can see that 4 equations and 4 unknown. Okay, now, so which means that the free node I have fixed as a node 1, that is because there is a displacement boundary condition that is 0. So what it will do is it will create a free nodes, that is you can see that is 2 3 4 5. Okay, these are free nodes, which means that, yeah, so now I will get k reduced matrix. Okay, what is the k reduced matrix? This part, this is the k reduced matrix, this part. Okay, that is 4 by 4 matrix. Okay, now it will solve. Okay, you can see that is f inverse, sorry, k inverse f reduced, so we will get u reduced. Okay, now it will substitute into the displacement vector. Now you will get u, you can see that this is u. Okay, and then we will get f reaction force, that is nothing but the k global and u minus f global. Okay, now it will display nodal displacement and all reaction forces. So code is done. Now we will match our results, whatever we got. Okay, so here the problem number 1. So the first problem, it is saying, where is that? Yeah, what is the element 1? Where is that element 1? Element 1, K11, that is 0.8711 into 10 raised to the power 7, which means that this is your correct answer. Okay, now the second part is saying K1, but that is 2 3 index, 2 3 index. Okay, 2 and third index, which means that minus 0.9956, which is closer to this. Now it is saying element 2 and index is 2 2, that is 4.44, so this is the correct answer. Now element 2 2 3 minus 2.22, so this is the correct answer. Now it is saying 3 3, so 1.944, so this is the correct answer. Now it is saying if K represents a global stiffness matrix and Kij are the components of global stiffness matrix, okay, then this is our global stiffness matrix. Okay, so what is the 2 2? So 2 2 is 1.911, okay, into 10 raised to the power 7, so this is the answer. K44, so this is K44, that is 4.44, so this is the answer. Now K13 1.24, so this is the answer. 9 problem, it is saying K25, K2 and 5, that is 0. Okay, so this is the 0. K34 minus 2.22, so this is the answer. Now it is saying solve Ku equal to F. Okay, we already solved that. It is saying displacement of the material junction. Okay, what is the material junction? Material junction is at node 3. Okay, nodal displacement material junction at node 3. What is the answer? 1.9. Okay, it is saying 0 mm, so okay, so that's why this answer is 1.9. Okay, what is the displacement at the right end? Okay, at the right end means what is the node? Node 5, that is this answer. Okay, 0015, that is, which means that this is our answer. Reaction force at the left end. Okay, reaction force at the left end 10 raised to the power 3. Okay, reaction 10 raised to the power 3, which means that it is asking the in kilonewton, that's why this is the answer. Okay, so this is all about the assignment solution. Okay, see you next week and we will try to solve assignment 5. Okay, bye bye.